Greetings and welcome to Distilled. In the previous lectures, we had started solving this problem where we had this kind of a reaction: A plus B gives C plus D. And we had mentioned that the rate of this reaction is given as KCA to the power N CB to the power M, where K is the rate constant, N is the order with respect to A, M is the order with respect to B. And then we had started solving this problem. So the first step was to start understanding the data. So basically reading the data. So we had data in the form of time and the concentrations of all the time and concentration of all the species, right? This was the data that we had with us. So the first step was to read all of this data uh, into our Python file. The next step was to convert this data in this form, in the form of minus RA versus CA, CB, and so on. So in order to get the rate of the reaction, we used numerical differentiation. So we had talked about forward difference method, backward difference method, and central difference method, right? So all of these we had worked on, and then we had said that since the forward difference method requires the point itself, the value of let's say CA at the point itself and a point ahead of it. So we mentioned that at t equals to 0, we would use forward difference method. The central difference was more accurate, so we preferred using the central difference method for all the other points. While for the last point, we used backward difference method because it required a point before uh, the the given point, right? So that's what we had done. So this was from the previous lecture. Now in today's lecture, we now have a rate of the reaction, we have the concentration of the species. So now we could go on to perform what is called as multiple linear regression. So in this video, we'll be talking about multiple linear regression. So we have already talked about linear regression. So when we talked about linear regression, we said that we are trying to fit a line, something of this type, to X versus Y data, right? So we had X versus Y data points, and we tried to fit a line to this data using multiple linear regression. And we used certain metrics such as R squared to characterize how good the fit is, and so on, right? The second thing that we did to derive these parameters was that we defined something called as the sum of squared errors, which was basically the given data point. So let's say yi minus the model that we were trying to fit. So that was beta naught plus beta 1 xi, right? And we evaluated its square, and we tried doing this thing. So I just maybe shift this thing here. So we did this thing for all of the data points that were available to us, right? That is how we evaluated the sum of squared errors. And the objective was to minimize the sum of squared errors with respect to both the parameters, right? And using this, we evaluated the parameters beta naught and beta 1, right? So that is what we had done for a simple linear regression model. We do the same thing for multiple linear regression as well. So in multiple linear regression, we don't have just one variable X. So by the way, this is known as the independent variable, and this is known as the dependent variable, or more often, this is called as a target variable, right? So in in multiple linear regression, we have more than one independent variables. So what we have for this is something of this kind: y equals to, say, beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus, say, till beta m xm, right? That is what we have for multiple linear regression. And once again, we define something called as the sum of squared errors, which is nothing but, so okay, so more easy to do would be to just define this as a different variable. So let's say y hat, this is the model or prediction, right? So and if I say y, so y is going to be the data point, right? So, and once again, x1, x2, x3, all of these are also data points. So these are all data points, right? But y hat is actually a prediction. So if we have, let's say, the parameters beta naught, beta 1, and so on, then using the data points x1, x2, x3, and so on, we'll be able to predict y hat. But y is what is known from the experiment or from the data that you have, right? That is known. So we need to evaluate y hat. Basically, we need to minimize this thing, y hat I minus y whole squared, sorry, yi whole squared summed over all possible data points, right? So we are basically trying to minimize the difference between the prediction and the actual value or the true value, right? So we are trying to minimize the difference between the actual value and the predicted value, right? So that is what we are trying to do. And once again, that's what we can do. So we can get the derivative of this SSE with respect to each beta and set it equal to 0. And when you do this thing, so people can use Einstein's summation convention over here, which is another way to sort of write summations, and it makes your calculations of such complex matrices very easy. But altogether, what you finally get from this is that but before I go to that, so basically you'll be able to get the solution, the values for beta, and I'll just write down how to get these values, right? So in order to get these values, we'll define a few vectors. So let's define a b vector. B vector is nothing but a parameter vector. So this is a parameter vector, and this contains all the parameters in our model. So beta naught, beta 1, beta 2, and so on till we have till beta m. So beta m. So this vector, the size of this vector is m plus 1 cross 1, right? Okay. And then we have something called as the X matrix, right? So the X matrix contains, the first column is a column of ones, right? The second column is the values of the variable x1 at all the data points. So this would be x1, 1, which means the value of the variable x1 at the first data point. This would be x12, value of the first variable at the second data point, and so on till x1n, because we have n data points. And similarly, we can do this for all the m variables. So we have xm, which has xm1, xm2, and so on till xmn, right? And once again, the size of this vector, so this has m plus 1 columns and n rows. So this is n cross m plus 1, right? That's the second matrix that you need to define. And the third matrix is, or that is not a matrix, that's again a vector, y. So that is going to be y1, y2, and so on till yn. Okay. By the way, this is known as a feature matrix. because x1, x2, x3, all of these are features, right? And this is known as the target variable, or this is a vector of target variables. So you can call this a target vector. So this is the target variable, the vector of all target variables at all the points. And the size of this is n cross 1, right? So, and the predicted y, let's say a predicted y. So let's say that's a yp vector. So if you see from the top over here, this equation, so we can write the predicted y as a in the form of a matrix multiplication. So we can write that as maybe something like B transpose. So that becomes a 1 cross m plus 1 times x vector transpose, right? So that becomes m plus 1 cross n. So I'll just write down here maybe. So this is 1 cross m plus 1, and this is m plus 1 cross n. So this actually gives you yp vector, which is 1 cross n. And let's say we want it in n cross 1 form. So we'll also take a transpose of this. So that's what we get over here, right? So that's how you get the predicted vector. And we need to minimize and maybe the sum of all of these, right? This is what we need to minimize. So when we do that, we get the, so I'll just directly write the formula over here now. So we get the parameter vector B as x transpose x. So x transpose times x whole inverse times x transpose y, right? So let's see if our the way we have written it is correct. So since x transpose is, so x is n cross m plus 1, so this is going to be m plus 1 cross n. This is n cross m plus 1. This is once again m plus 1 cross n. And this over here is n cross 1, right? So this all together, so these two when they are multiplied, this gives you m plus 1 cross 1 vector. And this gives you m plus 1 cross m plus 1. So finally, you get this b vector as m plus 1 cross 1, right? So, and that's what we have, the b vector, which is m plus 1 cross 1. So that makes sense. So this is the formula that we need to remember. This can be derived, but that would require you to use maybe some matrix algebra, some Einstein summation convention. So I'll not go through the derivation here, but this is the formula that you need to use. Okay. And this is how you form these matrices. All right. So we have a matrix X, we have the vector B, we have the target vector Y, and that is where we use all of these, right? So now in this lecture, we'll be learning a few interesting things. First, we'll be learning how to take a transpose of a matrix. Second, we'll be learning how to multiply two matrices. Third, we'll be learning how to take inverse of matrix, right? So we'll use all of these three concepts here, and we'll try to evaluate the vector B over here, right? So that is the objective. So now let's go back to Python and see what we can do with it. So far, what we have done over here is that we have imported the libraries pandas and numpy. We have been able to read data from our Excel file using pandas. After that, we uh, performed numerical differentiation in order to get the rate of the reaction, right? That's what we have done. And that's basically minus RA over here. Now, since our reaction is of the form, rate of our reaction is of the form minus RA equals to K Ca to the power n Cb to the power m. So in order to convert this into a multiple linear regression sort of a problem, we'll take a logarithm both sides. So my ln of minus RA is equal to ln K plus n ln Ca plus m ln Cb, right? So over here, we see that this over here is the target variable, say y. This over here is the first feature, x1. This is the second feature, x2. And these are my constants. So beta naught, beta 1, and beta 2, right? So that is what we have over here, right? So now, since we have a clear picture in our mind, let's go ahead and try to evaluate or at least start preparing these vectors. So let's start with the vector y, the target variable over here. So to do that, now that is why NumPy becomes very easy, because you just have to type np.log and the name of the array, right? So since we have to take the logarithm of minus array is the variable where we store the values of minus array. So we just need this. So since array is a NumPy array, this operation would be applied to each of them, each of the values, and it would be stored as an array. And this array would be stored in the variable y, right? So y is now an array of log array, log minus array, right? Similarly, we have the next variable x1, which is np.log ca. We've already read ca over here, right? And x2 is np.log cb, right? So that is what we have so far. And after that, let's prepare our matrices, right? So first we need to prepare the X matrix, right? So how to prepare the X matrix? So remember, in the X matrix, we had this thing. We had a column full of ones, then we had a column of the X1 feature, then we had a column of X2 feature, and so on. So we need to actually merge these two columns and prepare another column of all ones, right? That is what we need to do. So let's start by preparing a column or basically an array of all ones. So NumPy actually makes it very easy. So let's call that array a constant array, const. So that has to be all ones. So you can just say np.ones and you can specify the length of the array. So if you want it to be a two-dimensional array, this has to be a list. Basically, it has to have two values. So let's say if you want a 2 cross 2. So I could show it over here maybe. So let's say if I want a 2 cross 2 array. So that is what it gives me. If I want, let's say a 3 cross 2 array. So it gives me an array of 3 rows and 2 columns, right? But if I just say np.ones 3, that just gives me an array of ones with 3 values, right? 3 ones, right? So this just gives me a value of an array of ones, and the size of that array is whatever is the length of the CA array, the number of data points that we have, right? So now that is also done. Now we need to prepare the X matrix. So let's call it X, just X. And now we have to merge these three columns. So the first column has to be const, the second column has to be X1, the third column has to be X2, right? So this is what we do for that. np.column stack. So this stacks 1D arrays as columns of a matrix, right? That is what it does. And inside it, you'll have to give within circular brackets, you'll have to give column names. So the first column has to be the column of ones, the second column has to be the column of X1, and the third column has to be the column of X2. So if we run this, we'll see over here, the matrix X has been prepared. So this has all the columns. This is the column of ones, this is X1, this is X2, right? So that has been prepared. So with that, we can then move on and try to, so this is how you make the column matrix, the matrix X, right? So if you have, let's say, if you want to prepare a matrix and you have all columns and you want to merge all of them, this is how you do it, np.column stack. Similarly, you can use row stacks. And if you make a row stack, let's just try that out. So if I make a row stack, so in that case, X constant as in ones, X1 and X2 would be the rows of this matrix, right? So that's what you have over here. So this is not something that we are going to use. So I'll just remove or just comment this out. And so that's the X matrix over here. All right. After that, we could move on to multiply these two, right? So we have to, so first of all, we need the transpose of X, right? So to get the transpose of a matrix, we once again use np.transpose, and that gives you the transpose of a matrix. So if I call this matrix, say xt, that would give me the transpose of the matrix. So we've got this matrix over here, right? That's the transpose of the matrix X, right? That's how you calculate the transpose, as simple. And after that, we need to multiply the two of them. So we need to multiply X transpose to X. So to multiply, so this is matrix multiplication. So all that you need to do for matrix multiplication is you have to use np.dot, that's what you use. So np.dot, and then when you write the two arrays, so this would carry out the operation xt multiplied by x. That is the operation that this would carry out, and we need to store this somewhere. So let's call it x transpose x, right? So that's matrix multiplication, right? Next, we need to calculate the inverse of the matrix. So similar to the linear algebra thing that we used in calculating the in solving the system of linear equations, we are going to use the same thing. So np.linear algebra, and to solve we would use this, right? But here we just need an inverse, so we could say inv, that gives you the inverse. So np.linalg.inv, that gives you the inverse of matrix. So we need the inverse of x transpose x. So that is what we have, x transpose x inverse. That is how you calculate the inverse. So when you do all of this, you see the x transpose x inverse has been calculated here, right? Next thing that you need to do is you need to multiply this entire thing to x transpose y. So this was the formula that we were using, x transpose x whole inverse times x transpose y. So let's just calculate x transpose y somewhere. So once again, x transpose y is np.dot a dot product between X transpose and the target vector Y, right? So that gives you X transpose Y. And finally, we need to multiply X transpose X inverse to X transpose Y, right? So that gives you the B vector. So B is equal to MP dot X transpose X inverse times X transpose Y. So that is the parameters. And that is all. These are the parameters of our problem, right? So this is ln k. This is your n, and this is m, right? By the way, the actual answers for this problem were k equals to 2, n equals to 2, and m equals to 1. So as you see, they've very closely matched these three. So let's just try and see where we are with this. So maybe k would be np dot exponent of b1, right? Because this is ln k, so k would be e to the power whatever we've got, and n would be b, sorry, this is not b1, this is b0 over here. N would be b1 and m would be b2. So if you see, we have the rate constant is 2.425, which is again close to the rate constant value of 2, right? This also depends on the nature of the data that you have, the number of data points that you have. So for example, here, maybe the case was that since the reaction was taking place fast enough, because of that, the way we've calculated RA might not have been the most accurate way. But still, we've been able to make good enough prediction. So at times, data itself limits us, but whatever we have is good enough, right? And one thing that you would want to do is to compare how well your solution has performed compared to a given data. So one thing that people often do is try to plot something called as a parity plot. So first of all, let me just import the library for plotting stuff. And then let's see what is a parity plot. So parity plot is the plot you plot between the predicted variable and the actual data. So for example, in this case, we had the target variable y, which was ln minus ra, and we tried to predict something which was predicted using this formula. So we predicted y equals to b. This is how you predict this. So b transpose x transpose, and the transpose of the whole thing gives you the predicted variable, right? So you plot yp versus y actual, right? Now ideally you would want them to be equal. So therefore this diagonal, which is y equals to yp, this is where you want your data points to lie, or the plot to lie. So the deviation wherever your data points lie, it should be somewhere close to this. If your data points are lying somewhere here or here, that means your data has not really fit very well. So this is known as a parity plot. And if you work on machine learning or data analysis for that matter, you will be using parity plot very often. So this is something that could be of interest to some of you. So let's see the parity plot over here. So for that, we need to get y predicted. So let's get y predicted. So y predicted is the vector b multiplied by the transpose of vector B multiplied by X transpose. By the way, this is a very common, this is something that you would know from matrix properties. So AB whole transpose is B transpose A transpose. Hopefully that is clear. So therefore YP can be written as B transpose X transpose whole transpose, which can be written as X transpose transpose B transpose, which can which can be written as X multiplied by B. So that is what we'll evaluate over here. X multiplied by B. So NP dot X multiplied by B. So that's my Y predicted. So that's the values of Y predicted that I've got. And now let's try to plot the parity plot. So PLT dot plot Y comma Y predicted. So this would have my Y. This would have my Y in the X axis and Y predicted in the Y axis. And let's just plot the diagonal as well. So PLT dot plot, actually we'll scatter plot this thing. So PLT dot scatter, this prepares a scatter plot of this prepares a scatter plot of Y versus YP. And let's just prepare the diagonal, which is Y comma Y, and PLT dot show. Right. So that is what we are going to plot. So let's see the plots over here. And you see over here, the data has actually fit really well, right? If I could zoom this in somehow. Yeah. So the data has actually fit in very well. So this is the diagonal and the scatter points are almost on the line everywhere. So this data has actually fit in very well. And that is how you can see how how this model has performed. So hopefully it was fun solving this problem. We had, once again, I would just give you a recap. We had a data for time as a function of CA, CB, and so on, right? CA, CB, CC, CD at all different points. So first we read this data, we got the time values, concentration values. After that, we used that to calculate rates, which was done by evaluating numerical derivatives. And then we used multiple linear regression to evaluate these points, right? We used multiple linear regression to evaluate the rate constant, the order of the reactions, and so on and so forth, right? So this gives us information about the kinetics of this particular reaction. So now we have the reaction A plus B gives C plus D, and we knew that this follows this kind of a kinetics. Sorry, Ca to the power n, Cb to the power m. So we knew this kind of a kinetics is followed. So now we have all these parameters. So we have all the information about the kinetics of this reaction. Now further, we can use this information to evaluate concentration of A, B, C, and D at more times. Let's say, so this data that was available was till time t equals 2, but we could go ahead and evaluate it till time say t equals to 10 and see what's happening. So we would do that maybe further on in the next video, but hopefully so far it has been helpful. In case you have any doubts with how I did any of these things, if you want lectures on any of the steps that I've followed in more details, you could please mention that in the comments section, or you could just mail me and I would try to provide that. Thank you so much.